Well, folks, guess who shows up at my house?
So I get to be the one on camera.
Yeah, you're the one on camera. I'm back here. Nobody gets
camera.
to see me.
Yeah.
And we're going to do some experiments this weekend.
Yes, we certainly
are. And you all will be the lucky ones to view the experiments Ben and I are going to do.
Yes, absolutely.
So let's get at it. Let's do it.
Absolutely.
Peace. Okay, today's test, I've got material suspended above the test bed, and we're going to turn the current on before we start. Have it attached to a vibrator, which will disperse the sand on a somewhat consistent basis. And so we'll turn the current on. As you can hear, we'll drop the electrodes down some. And then I'll start to allow the material fall from above. We'll observe. You see that we do still get the same tight patterns, whether the material was placed down below or from above. See that over there?
You want to run it wide open? Let's see if we can move what's down there already.
It is with this 70,000 volts. We can increase it by dropping the electrodes a little bit. That button. We'll put some more down there. Notice that area in the center where we have perpendicular motions there.
And you can tell that the...
And another thing, this is a mixture of lime or dolomite and clay.
You can tell the fine powdery stuff is the dolomite, right?
Right, the light-colored powder, and the thicker, heavier granules are clay. And you can see they're separated quite nicely. A lot more clay distributed around the outside versus the dolomite, which tends to stay in the center. See if I can zoom into some of that. On the other side, that is so incredible. And this is that motion where I want to tell you, they call it corona. It's a coronal field there, and that is where the dendritic, ranges, mountain ranges, and patterns will show up, along with all the other features. In my opinion, that right there is where the mountain ranges will form at this scale, which is where we see the Lichtenberg figure. See it there?
Yeah. Almost looks like Laniakea and the Perseus Pisces cluster.
And notice the bar S shape feature that's forming now. This happens almost every time between, you end up seeing this yin and yang symbol. See?
Yeah.
Which is seen all over the planet, really. If you start looking and know what to look for, you'll see these types of features all over our planet. The west coast of the United States. Michael Steinbacher's noted it around Afghanistan, which is to the east of Giza Plateau. I don't know if you know anything about it. That's where they're reported seeing the pillars in the sky, where it's to the east from Giza.
Yeah.
When you look geologically, you see these type features there. All over northern Africa, these type of features are there. In the Sahara there.
Want to try something?
Sure.
Let's turn it off. And can we spread out?
Notice something too.
Wow, we've turned it off and they're still going.
Yeah, they'll stay that way for quite some time. They will go down. Zoom in so that people can see this.
It's even still going on that side too.
Yeah, And that shows that that acrylic sheet is you know, capacitizing or holding some of this charge.
Can we spread the electrodes apart a little bit?
Sure can. Let me get this camera set back up shut. Better. Look at that.
Wow.
Look how intricate those patterns are. That's incredible. And again, I can't believe how much separation we see there. That's incredible too. I just closed the camera.
It's not so bad, really.
Yeah. Turn
Fire
it
it back on?
Ready?
Yeah.
3, 2, 1. Again, we've kept it at 70,000 wide open the entire test, so yeah, do that. Some more down. See, notice those void areas don't change at all. No material filled up those voids. Keep doing it. See? In fact, it just compounds it. It keeps, the material continues to land in the same areas, avoiding the same areas. See it?
Yeah.
Watch, I'll turn the current off. You keep going. And you'll see now we're going to start filling them right up.
And especially over there, those are filling up really fast. Alright, go ahead. It's got to work to make new connections now. That's interesting.
Let's,
Oh, I wish people could see that.
what are you looking for?
Stuff coming up. Might have to drop the camera down all the way here.
Close to the edge.
Oh, you're also sparking on that thing.
My lamp.
Yeah. Yeah, can we bring that, bring it back up over the hill there, because it's pulling stuff up to it.
Yeah, they'll do a better job of getting loaded together. Maybe not that close.
Oh, look at that. Look at that.
What?
See it lifting up underneath there?
Yeah, well, we have that recorded quite a bit.
Yeah.
Backed it in all the way and knocked all the crap off. At any rate, you can see that bar S pattern show up right in the center of everything. That almost every time we do this, whether we put the test, you know, with the material down on the plate first or drop it
Can
from
you
above.
zoom in on there and see how fine those lines are?
Yeah.
Those lines that are in there, that are forming, they're lines of single file particles.
Look how intricate it is here in the finger just for reference. It's sharp. At any rate, that's a cool one.
Yeah.
Peace out. me see it.
I want to bring it down here again so people can see the mist rising up on the lower throat.
It's hard to make out, you know.
Yeah, it's better on the other one. A lot better on the other one.
Oh, yeah.
Yeah, put it against the black background.
Can't get this thing to go over any further. It won't go down. Need to just take it off of that. And that doesn't appear to be doing it anymore.
That's very strange.
Oh, I see why. See, the water's connected to
Yeah.
the conductivity at the bottom.
See what happens if you raise it up a little bit.
It'll break it. And it goes back. See it lifted right back up on it. Maybe I could technically switch it off. Slide this over some. Yeah, now we can see it better.
Oh, that was
Draws it
great.
right up, doesn't it?
Yeah. That was terrific.
So according to this test, we have an anode on the right, a cathode on the left. In the northern hemisphere, magnetic influence would suggest that the left side is the high pressure side, which we see evacuation of water vapor. In the right hand side, which is counterclockwise rotation, is accumulating or drawing in moisture. At any rate, this is around 50,000 volt discharge between the two. And that's just ordinary tap water with some salt in it.
What are you using to make the mist?
These are pond foggers, what they're named.
How do they turn the water
They
into
use
mist?
ultrasound, ultrasonic, little metal speakers, actually. Create an ultrasound, causes a water vapor.
Have you tried this using the plate?
Just the iron plate.
No, just where you have one thing coming down that's discharging, and then you ground the plate.
Oh, well, yeah, but again, we get that barrel roll then,
Yeah.
say. When we try to discharge directly between the anode and cathode, the rotation is perpendicular to the axis of discharge.
Gotcha.
Yet when we rotate anode and cathode down to a third conductor, which would be this plate, this acrylic sheet, then it seems to isolate the rotations. See, one's... In other words, they're counterintuitive to each other, I think, in my opinion. I have to loosen that handle there. And as you can see, as it continues to run, the more water that builds on the table between the two makes more of a conductive path, which doesn't allow it to do what it normally did, which was go through the air. So we'll stop the test in a second, try the table off. I'll lift the anode cathode up a little bit higher.
You are going to turn it off before you wipe the table down, right?
Yeah, just going to kind of see what it's doing. So the effects are much different over water than they are over.
Oh. Can we stop this recording just so we save the time?
Yeah. Okay, this test I have a couple of 2-inch sphere magnets. They're N52, very, very powerful magnets. They're not considered toys. And Ben's going to sit and oscillate one magnet in his hand. And again, they're both oriented with the poles up, facing upward, both north poles, so they're in a repulsion mode. And if you just oscillate one it will cause the other one to rotate, as you can see. And they're hanging with fishing lines so that we don't have any type of torque on the string. And then we want to take a look. If you take one of these and apply electric current to it, you get what you call a homopolar motor. You apply DC current to the pole, one of the other poles, and the equatorial region of the magnet.
Probably got to tilt this a little bit.
There she goes. That's in there. And you can see you get the magnet will rotate with just a very small, this is less than 2 volts of electricity.
What happens when you take this down, put it on the bottom?
Yeah, if you put the electrodes at both poles, you won't get any rotation whatsoever. It really only works between the
tropics.
The tropic regions, yeah, the 19.5 up and down latitude, north and south. Of course, it will get running away there and fly off the table and injure one of us. Yeah, this is the homopolar effect, homopolar motor.
Awesome.
Yeah, that was really awesome how we could just oscillate one and cause the other to rotate. That was incredible. I don't know if it'll do it there. Try it. There's still Noah Poop that's trying to flip over. You see it? Yeah, it's coming after you. At any rate, that's a cool one. I think we flipped it over, didn't we?
We did.
Yeah, they're attractive now. Anyway, peace
How
out.
am I going to do this without hurting myself here? Alright, Billy, so we have these two pieces of metal here. We got this wire going through the center, and what we're going to do is we're going to magnetize these to the point where I can't pull them apart. And my question is, why is this different than, wrapping the thing around a nail and magnetizing the nail? I mean,
to be honest, I really don't know. It makes very little sense to me. But yeah, if we just pass a conductor between two pieces of iron and apply, this is just a 12-volt battery, DC battery, a little switch, and that just a small current through it. You'll see these are now literally, I mean, it'll take a few pounds to pull that apart. You literally have to turn them to get them to come apart. In my opinion, this is not normal. You need a coil. Matt Emery's perpetual motion holder, for instance, has coils on both sides of the horseshoe that creates the same effect with the capstone, so to speak.
What's interesting is this is insulated as well.
Yeah, the wire's not actually touching the metal. It's an insulated wire. In fact, if you use a raw wire, this process won't work.
No.
It's this magnetic field that this produces is causing that magnetization in the metal.
We do it with this
and
one
again,
too.
if we turn it, we get them apart, and they're no longer magnetic anymore after you break that. Just like Matt Emery's. And yeah, this actually works on many surfaces. And you really don't have to have all this switch. You can just touch the contact right there to the battery on both sides, and you see that it's substantial. And again, once you break the bond, it no longer does it until you put a charge across it again.
Will this work?
Touch that one while that one's doing. Let's try it and see. Break that loose. That's loose right there.
Mm-hmm.
Make sure it's touching. Didn't seem to work in that. It did here though.
Let's try
again. If we try this in different configurations. It's fairly strong.
For example, though, if this was like this, you couldn't put it on the side and have it work, right?
Mm-mm. center though.
Now, Billy,
So that's pretty incredible. Now,
let's try the hard one.
yeah, by the way, I saw this guy on, called RWG Research. His guy's name is Russ. He has a YouTube channel and a web page, which is RWG Research. And I saw him do this with these nuts right here. So hats off to you, Russ. And I thought that was pretty cool. That's what started me, getting me interested in looking into what was causing this. I found that you can actually just use anything really. But if we take this that off of there before we have a meltdown wire and pass it through the center of these nuts here.
I can hold it.
And that would just touch it to one side and then touch it just like that. With that piece of put the camera here. This will actually, if I do it right and I'm gentle and gingerly, they will stand themselves up. They'll stay together too. And of course they're not magnetic either. And once we break that bond, if they lose it completely, they won't go back up there until you charge them again. So it works on multiple surfaces. There's some sort of rotational energy involved there.
Now, it's not strong enough for me to pick it up, is it?
Yeah, it'd probably fall apart. Yeah.
But I could feel
You can feel it, yeah, absolutely. And now you can tell. You can touch it again, now you see they're non-magnetic whatsoever.
And there's no way to make those 6 stay in that position if they weren't connected. They fall off, right?
Nah, we try it if you want to.
Yeah.
They'll fall right over. It's easier when you have 2 at the bottom. As you'll see, as soon as you'll see how separate they are now. See? When you get close to staying up without it. So it's pretty cool.
Yeah.
The perpetual motion holder, you can look it up on Matt Emery's website. The theory to it, behind it, or whatever. Again, you don't need a switch. Those are right there.
Were you touching it when you did that?
Yeah. It's just 12 volts. This won't shock you. Our worst fear would be for that to get stuck and the wire would turn red hot, melt, burn me. Nonetheless, you see that? It does take me just a touch, just a small current to pass through that wire and create magnetic fields that bind iron substantially.
Now, if I hold it like this, I can still feel a little bit of the resistance.
Yeah, and that's another thing. These large plates, you can leave them on overnight, and you can feel a lot of residual afterwards, residual magnetization. So they do somewhat after a time, over time, retain some magnetism. It's so cool.